Welcome to the deep dive. We take your trickiest topics, the stuff you're trying to wrap your head around, and we dive deep into the source material to pull out the essential insights.
Yeah, get right to the core of it.
Exactly. Today, we've got a request that takes us right back to, well, the foundations of math. A listener sent us the Pre-Calculus Equations and Answers Quick Study Guide.
Ah, one of those laminated guides. Very useful.
They are. And our mission, which we've enthusiastically accepted, is to explore the core ideas of pre-calculus. We're aiming to give you a clear and hopefully engaging understanding.
Highlighting those aha moments, maybe, and the surprising connections.
That's the plan. Build a solid base for more advanced math, all without getting, lost in the weeds.
Sounds good. Where should we start?
Okay, let's jump right into it with something fundamental, linear functions.
Absolutely. Linear functions really are where it all begins. As the guide points out, their graphs are simply straight, non-vertical lines.
Yay! Non-vertical is key.
And it's incredibly useful to understand the three different ways we can represent these lines with equations because, well, each form highlights different properties of the line.
Exactly. First up is the classic slope-intercept form, y equals mx plus b,
The one everyone remembers first.
probably.
Yeah.
Here, m is the slope. Think of it as the steepness and direction of the line, and b is the y-intercept.
Which is just where our line crosses that vertical y-axis.
Yeah. So a classic example from our source, y equals 3x plus 5.
Yeah.
Straightforward, right?
Totally. A slope of 3, and it intersects the y-axis at the point 0, 5.
Precisely. Now, what if we don't know the y-intercept directly, but we do know the slope and maybe just a point the line passes through?
Ah, that's where the point-slope form really shines.
Yeah.
y11 equals mx by 1.
Okay.
Here,
Yeah.
m is still our slope, no change there. And ac1, y1 is that known point on the line. The guy gives us y plus 4 and gas to 2 by 6.
So from this, we can immediately see the slope is metis to 2.
Right.
And the line goes through the point, 6 net is 4. It's like having a treasure map with a landmark and a direction.
I like that. A mathematical treasure map.
Yeah. And finally, we have the standard form. X plus bi equals c. Now, at first glance, this one doesn't immediately shout out slope or intercept, does it?
No, it looks a bit different. But the guide reminds us that the slope is actually AB.
Ah,
Right.
okay, yeah.
And the y-intercept is CB. Plus, there are these rules. A has to be a positive integer, and A, B, and C are all integers. No fractions hanging around in the main equation.
Okay. What's truly elegant about the standard form, though, is how easily you can find the intercepts.
If you want the x-intercept, that's where the line crosses the x-axis, right?
Yeah.
You simply set y to 0 in the equation and then solve for x.
Easy enough.
And conversely, set x to 0 to find the y-intercept where it crosses the y-axis.
Okay, let's use the example. 3x plus 2y equals 4.
Right. As we set y to 0, we get 3x whole 4. So x equals 43. That's our x-intercept, the point 43, 0.
Brought it.
And setting x to 0 gives us 2y or 4, so y equals 2. That's our y-intercept, 0, 2.
Nice. And you can also see how they derived the slope using that formula in AGB, which is negative 32.
Exactly. And the y-intercept CB is 42, which simplifies to 2. It all matches up.
See? Standard form isn't so mysterious after all. Okay, let's move beyond straight lines to the world of curves. Polynomial functions.
Okay, things get a bit more interesting here.
These look a bit more complex with their general form, fx equals xn plus bxn-1 plus cxn-2 plus dx plus e. Vertelli.
Lots of terms, potentially. But the most insightful thing to grasp initially is the degree of the polynomial.
And that's just the highest power of x in the equation, right?
Exactly. It's like the lead actor in the polynomial drama. And as the guide highlights, the degree tells us something fundamental about the real zeros.
The zeros being where the graph crosses the x-axis.
Precisely. If the degree is odd, like a line degree 1 or a cubic curve degree 3, you're guaranteed to have at least one real zero. It has to cross the axis somewhere.
Because it goes off to positive infinity one way and negative infinity the other way, eventually.
Basically, yes. But if the degree is even, like a parabola, degree 2, or a quadratic, degree 4, it might hover entirely above or entirely below the x-axis.
So it might have no real zeros at all.
Correct. It could have 0 or 1 if the vertex is on the axis, or 2 or more up to the degree number.
That's a neat trick to know right off the bat. It gives you a sense of what the graph might do. And the guide also mentions imaginary roots. using I.
Yes, the guide touches on imaginary roots. Now, this might sound a bit out there, but sometimes when we solve equations, especially quadratics or higher degrees, we end up needing the square root of a negative number.
Right, which isn't a real number.
Exactly.
Hmm.
So mathematicians introduced the imaginary unit I, which is defined as the square root of -1. So imaginary or complex roots involve this special I.
And these can show up for both odd and even degree polynomials.
They can. So even if an odd degree polynomial has to have at least one real root, its other roots might be complex. An even degree polynomial might have only complex roots. They always come in pairs, actually, complex conjugate pairs like a plus bi and a bi, if the polynomial has real coefficients.
Okay, that's heading a bit deeper, but good to know they exist. Let's zoom in on a specific and very common type of polynomial: quadratic functions.
Ah, yes, the parabolas.
We all know these, the fx equals x2 plus bx plus c crowd, where a can't be 0. What are the key characteristics we should immediately be aware of?
Several key features define quadratics and their parabolic graphs.
Huh.
First, there's the axis of symmetry.
The mirror line.
Exactly. It's the vertical line x both discal b2a that cuts the parabola perfectly in half.
Okay.
Then we have the y-intercept, which is super easy in this standard form. It's just the constant term c. It's where the parabola hits the y-axis at the point 0, c.
Right, and we can also write quadratics in vertex form. Fx equals a xh2 plus k.
Yeah.
This form always felt like a cheat sheet to me.
It really is. It's incredibly informative because Liscula k directly gives you the vertex coordinates.
The turning point.
Yep, that peak or valley. And the a value, the same a as in standard form, still tells you whether the parabola opens upwards, if a 0, like a smile,
Yeah.
or downwards, if a 0, like a frown.
So useful.
Also, and this is important, the guide reminds us that a parabola opening left or right isn't a function.
Because it would fail the vertical line test?
Precisely. One x value would map to two y values.
Yes.
And crucially, that vertex, hk, is the critical point where the function's behavior changes, from increasing to decreasing, or vice versa.
Okay, so we understand the shapes, but how do we find those all-important roots, those x-intercepts where the function equals 0? Our guide lays out a few methods.
It does. The simplest, when it applies, is using square roots.
When does that work?
It works perfectly if you have a quadratic equation where the bx term is missing, something like by 2, 9 equals 0.
Oh, okay.
You can just isolate the by 2 term, so by 2 is 9, and then take the square root of both sides. Just got to remember.
Both positive and negative.
Exactly. Don't forget the plus or minus. So you get x to 3 or x equals misses the 3. It's a quick win when the structure is right.
Makes sense. Cut right to the answer. Then we have factoring. I vaguely remember struggling with this back in the day.
Yeah, it takes practice. If you can factor the quadratic expression into two linear factors, like the example by 2 plus 2 by 8 equals 0,
Which factors into?
x plus 4 by 2 equals 0,
Mm.
then each factor gives you a root, because if the product is 0, one of the factors must be 0.
Right.
So setting x plus 4 leads to x equals 4, and setting by 2, 0 gives x equals 2. The guide notes this is particularly useful when the constant term, the ocan 8 here, has only a few integer factors to check.
Makes the trial and error manageable. But what if it doesn't factor easily? Or maybe it looks like it won't. That's where the trusty quadratic formula swoops in to save the day, right?
Absolutely. The quadratic formula, x equal b g2 4ac 2a, is your universal tool. It works every single time for any quadratic equation.
Even if it doesn't factor nicely.
Especially then. It's your go-to when factoring seems impossible or just too time-consuming, like with the guide's example 2 by 2 plus 5 by 9 equals 0.
Okay.
Plugging in a2, b5, and c9 gives us x equals 5 minus 90 to 8, where dan is 12, 22, which simplifies to...
X as minus 5 manale, Danny 7, 4.
Exactly. It looks a bit intimidating maybe with the square root of 97, but it's the precise answer. It's a reliable workhorse.
And our guide also mentions completing the square as another method.
Yes, completing the square. It's another way to solve any quadratic, and it's actually the method used to derive the quadratic formula itself.
Ah, interesting.
It involves manipulating the equation algebraically to create a perfect square trinomial on one side. The guide briefly shows how by 2, 8x plus 3 can be transformed. You move the constant, take half the coefficient of x, that is 82, x equals 4 is 4, square root of 16, and add it to both sides.
So you get by 2, 8x plus 16 equals 3 plus 16.
Precisely, which becomes by 4, 2 equals 13. Then you just take the square root of both sides, remember the plus minus.
The puff 4 equals 13.
And finally, x equals 4 till a 4 agents 13. It's especially handy, the guide notes, when the coefficient of the by 2 term is 1 and factoring isn't immediately obvious.
Okay, before we delve into more exotic types of functions, let's just quickly nail down the fundamental definition of what a function is. What makes a relationship qualify as a function?
All right, good idea. The core idea, the absolute definition, is that for every single input value in the domain, often our x values, there is exactly one corresponding output value in the range, often our y or fx values.
One input, one unique output, like ordering from a menu.
That's a great analogy. You choose one item, the input, say cheeseburger, and you expect to receive one specific dish, the output, the actual cheeseburger, not suddenly get a cheeseburger and a salad for the same single order.
Okay, that makes sense. No ambiguity in the output for a given input. And we have independent and dependent variables in this relationship.
Exactly. The input x is the independent variable. We can choose its value freely from the domain. The output y or fx is the dependent variable because its value depends directly on what x we choose.
And how can we visually tell if a graph represents a function? There's a test.
That's where the vertical line test is your best friend. It's super simple.
Okay.
If you can draw any vertical line anywhere on the graph, and that line intersects the graph at more than one point.
Then it's not a function.
Correct. Why? Because that vertical line represents a single x value, but hitting the graph twice means that single x value has multiple corresponding I values, which violates our fundamental one input, one output definition.
Got it. And the guide also reminds us that functions can be represented by equations, either like y equals 7 by 11.
Or using that fx notation,
Yeah.
fx equals 7 by 11. There's two different ways of saying the exact same thing. Fx is often preferred because it emphasizes the function aspect and makes it easy to show what input you're using, like f2.
Right, f2, 11 equals 3. Okay, now going back to that bit inside the quadratic formula, the part lurking under the square root, b2 4ac. Our guide flags this as the discriminant. Why is this particular piece so important?
The discriminant, it's like a mathematical fortune teller for quadratic equations. It's incredibly powerful because it tells us, without needing to fully solve the equation, how many real number solutions, or roots, the equation has.
Ah, so it gives you a preview of the answers.
Exactly. If the discriminant b2 4ac is greater than 0, positive, you'll have two distinct real solutions. The guide gives 2 by 2, 7 plus 3, where the discriminant is 7, 2, 4, 2, 3 equals 49, 24 equals 25. Since 25, 0, two real roots.
Okay, what if it's 0?
If it equals 0 exactly, you have exactly one real solution, sometimes called a repeated root or a double root. The vertex of the parabola sits right on the x-axis, like by 2, 8x plus 16 equals 0. The discriminant is 8, 2, 4, 1, 16 equals 64, 64 equals 0. One real root, which is come before.
And in the last case, less than 0.
If the discriminant is less than 0 negative, you have no real solutions. The parabola completely misses the x-axis. The solutions in this case are those complex numbers involving I. The example is 2 by 2, 7x plus 8, where the discriminant is 7, 2, 4, 2, 8 equals 49, 64, negative 15. Negative, so no real roots.
That's incredibly useful. Seriously, like getting the spoiler alert for the number of solutions before doing all the work.
It really is. It's a super efficient way to understand the nature of the roots right from the start.
Okay, let's move on to functions that look a bit more like fractions, rational functions.
Right. These are defined as fx equals px qx, where both px and qx are polynomials.
And naturally, the denominator qx can never be 0 because you can't divide by 0.
The cardinal sin of arithmetic. Precisely. That restriction is key to their behavior. What are the unique behaviors of these functions that stem from that?
Well, rational functions can exhibit some interesting breaks or discontinuities in their graphs. One type is called a vertical asymptote.
Okay, what's that?
It's a vertical line, say x equals c, that the graph gets infinitely close to on either side, but never actually touches or crosses.
And where do these happen?
These occur at the x values that make the denominator qx equal to 0 and don't also make the numerator 0 at the same time. The function is undefined there, and the graph shoots off towards positive or negative infinity.
Makes sense. Division by something incredibly close to 0 gives a huge result. What's the other type of break?
The other type is a point discontinuity, often just called a hole in the graph.
A hole.
Yeah.
Like a literal gap.
Pretty much. These happen when there's a common factor in both the numerator px and the denominator qx. You can cancel that factor out to simplify the function, but you still have to remember that the original function was undefined at the x value that made that canceled factor 0.
Ah, so the simplified function looks fine there, but the original had a problem. So you just draw a little open circle on the graph at that point.
Exactly. It's like a tiny point is missing, but the graph doesn't shoot off to infinity like it does at an asymptote.
Got it. Asymptotes and wholes, key features of rational functions. Our guide also briefly touches on how to manipulate these rational expressions, multiplying, dividing, adding, and subtracting them. Anything key there?
The basics are pretty much like regular fractions. For multiplication, you just multiply the numerators together and multiply the denominators together. Simplify if you can.
Yeah.
For division, you do the classic keep, change, flip. Keep the first fraction, change division to multiplication, and flip the second fraction. Take its reciprocal. Then multiply like before.
Right, invert and multiply.
Yep. Adding and subtracting is where it gets slightly trickier because just like with numbers...
You need a common denominator.
Exactly. The crucial first step is to find a common denominator for the expressions. The guide mentions using the least common multiple LCM of the denominators. Often, you'll need to factor the denominators first to see what the LCM should be.
Right, find the smallest expression that both denominators divide into evenly.
Once you have that common denominator, you adjust the numerators accordingly, multiply top and bottom of each fraction by whatever factor is needed, and then you can just add or subtract the numerators, keeping the common denominator.
Okay, so factoring denominators is often key for adding and subtracting. Makes sense. Let's switch gears again and talk about exponential functions.
All right. These have the form y equals abx. What's the deal here?
The defining characteristic is that the variable x is now up in the exponent. The base b has to be a positive number and not equal to 1.
Why not 1?
Well, if b were 1, then 1x is just 1 for any x, so ya1 equals a, which is just a horizontal line, not really exponential behavior.
Ah, okay. And b has to be positive.
Generally, yes, for the standard definition pre-calc. Dealing with negative bases raised to variable powers gets complicated quickly with complex numbers, so b0 and ba1.
Got it. What kind of behavior does this lead to?
It leads to the potential for very rapid growth or decay. If the multiplier a is positive and the base b is greater than 1, you get exponential growth.
Like the example y equals 25x.
Exactly. As x increases, you're multiplying by 5 again and again. The values skyrocket. Think of things like compound interest or population growth under ideal conditions, maybe even the spread of certain phenomena.
Right. It grows faster and faster. And what about the opposite effect? Decay.
If a is positive, but the base b is between 0 and 1, like a fraction or decimal less than 1, you get exponential decay.
Like the example y equals 4, 0.875x.
Yep. Here, each time x increases by 1, you're multiplying by 0.875, which makes the value smaller. The values decrease rapidly at first, then more slowly, approaching 0. This models things like radioactive decay, or the depreciation of a car's value, or how medicine clears from the bloodstream.
Okay. Growth when b1, decay when 0, b1. Now, what if we want to sort of reverse the process? Like, if we know the result, how do we find the exponent? That leads us to logarithms, right?
Exactly. Logarithmic functions are the inverses of exponential functions. They undo what exponentiation does.
So how are they defined?
The equation y log base x, read as log base b of x, is defined to mean the same thing as by x.
Ah, they're equivalent statements.
Precisely. The logarithm y is the exponent you need to raise the base b to in order to get the value x. For this to work nicely, both the base b and the argument x must be positive. Again, the base b cannot be 1.
Okay. The guide gives a good example. Log 2, 64 equals 6.
Right, because 2 raised to the power of 6 equals 64. The logarithm just isolates that exponent.
Yeah.
It's like asking a different question about the same relationship. What power of 2 gives 64? The answer is 6.
That makes sense. And then we have that special base e, Euler's number.
Yes, e. Approximately 2.71828. It's an incredibly important irrational number that pops up naturally in calculus and models continuous growth. The exponential function with base e, fx equal x6, is called the natural exponential function.
And its inverse is the natural logarithm, ln x.
Exactly. The natural logarithm, it is ln x, is simply the logarithm with base e. So ln x is the same as log x. It asks, to what power must we raise e to get x?
And they have that inverse relationship.
A beautiful inverse relationship. ln x undoes the exponential e, ln x, the exponential undoes the logarithm, assuming x is positive. Also, a handy identity to remember is that ln a1 because e1 equals e.
Okay. Logarithms can look a bit intimidating at first glance, but our guide provides some really useful properties and identities that make working with them much easier.
Oh, absolutely crucial for manipulating and simplifying logarithmic expressions or solving logarithmic equations.
Yeah.
One of the most practical is the change of base formula.
What does that do?
It says log bx, log b. It lets you change from any base b to a new base a, most importantly.
You can use your calculator.
Exactly. Calculators usually only have buttons for base 10 logarithms, log, which means log 10, or natural logarithms, ln, which is log. So the change of base formula lets you calculate, say, log 264 as ln,
Yeah.
ln2, or log 64 log 2. You'll get 6 either way.
Very handy. And those natural log identities we just mentioned.
Yes, lnx, lnx, and lne equals 1. These are fundamental for simplifying expressions that involve both e and ln. There are other log properties too, like logs of products, quotients, and powers, which are also super important, but maybe beyond this quick overview.
Got it. Now, what happens when we start putting functions together? Our guide covers basic operations with functions like addition, subtraction, multiplication, and division.
Right, this is pretty intuitive, thankfully. If you have two functions, say the guide's examples fx by 2 plus 2x plus 1 and gx equal 3 by 1, then f plus gx simply means you add their expressions together by 2 plus 2x plus 1 plus 3 by 1. Combine like terms and you get by 2 plus 5x.
Simple enough? Same for subtraction?
Yep. fgx means fx gx, so by 2 plus 2x plus 1, 3 by 1. Watch the signs when subtracting.
Right. Distribute the negative.
And you get by 2x plus 2.
And multiplication, f of g.
It means fx times gx.
Yeah.
So by 2 plus 2x plus 1, 3 by 1. You'd need to multiply that out, like using FOAL or distribution.
Yeah.
The guide shows it expands to 3 by 3 plus 5 by 2 plus by 1.
Okay. And division.fgx.
That's just the fraction of fx gx. So by 2 plus 2x plus 1, 3 by 1. The main thing here is the domain restriction. This new function is only defined where the denominator gx is not 0. So in this case, we're 3 by 1 euro or xa13.
Right, got to avoid division by 0. And then we have this slightly more abstract concept, composition of functions, written as fogx, fgx. What exactly is going on here?
Function composition means you're essentially plugging one function into another. You're nesting them. So fgx, which is read f composed with g of x, means you first evaluate the inner function, gx. Take whatever result you get from that.
And use that result as the input for the outer function, f.
Precisely. It's like a mathematical assembly line. The output of process g becomes the input for process f.
So for our example functions, fgx would mean taking the expression for gx, which is 3 by 1, and plugging that entire thing into fx wherever you see an x.
Exactly. So fgx, f 3 by 1, 3 by 1, 2 plus 2, 3 by 1 plus 1. Then you'd expand and simplify that.
Okay, that makes sense. Input of one is the output of the other. Now, what about the idea of undoing a function? That's where the inverse of a function comes into play.
Exactly. The inverse function, if it exists, essentially reverses the action of the original function. It swaps the input and the output.
So if f takes x to y, the inverse takes y back to x.
That's the core idea. If the point AB is on the graph of fx, then the point BA will be on the graph of its inverse, f1x.
That notation, f with a little -1 superscript, means inverse.
Yes. f1x denotes the inverse function. Be careful, it does not mean 1fx. That's the reciprocal. This is function inverse notation.
Got it. How do we find the inverse algebraically?
The standard method is 1. Start with your function, say y equals fx. 2. Switch the roles of x and y in the equation. Literally replace every x with y and every y with x. 3. Solve this new equation for y. 4. The resulting expression for y is your inverse function, f1x.
Okay, switch x and y, then solve for the new y. And there's a way to check if you found the correct inverse, right, using composition.
Absolutely. Two functions, fx and gx, are inverses of each other if and only if both compositions result in the identity function, which is just x.
So fgx must equal x, and gfx must also equal x.
Yes, both conditions have to hold true for all x in the appropriate domains. It's the definitive test.
The guide also mentions a crucial point. When is the inverse of a function also a function itself? Because sometimes it isn't, right?
That's a key point. The inverse of a function is itself a function only if the original function is 1-to-1.
1-to-1, what does that mean?
A function is 1-to-1 if no two different input values, x values, produce the same output value, y value. Each y value in the range corresponds to exactly one x value in the domain.
And there's a visual test for that too.
Yep, the horizontal line test. If you can draw any horizontal line that intersects the graph of the original function more than once, then the function is not 1-to-1, and its inverse will not be a function. It would fail the vertical line test.
Ah, okay. So like a standard parabola fx by 2 fails the horizontal line test, so its inverse, which involves the row x, isn't a single function.
Exactly. But a function like f is 2x plus 8, which is a non-horizontal line.
That passes the horizontal line test.
Right, so its inverse will also be a function. The guide shows finding its inverse. We
Right.
start with y equals 2x plus 8, switch to x equals y plus 8, y equals y, so y by 8 equals 12 by 4, so f1x 12 by 4.
And they verify it quickly with composition.
Yeah, of f1x 2 to 12 by 4 plus 8 plus 8 plus h plus 8, and f1f x plus 8 plus 8 plus 8 plus x plus 4 fours of x. Both give x, so they are indeed inverses.
This is all fitting together beautifully. Now, to help us make sense of all these different function types, our guide introduces the concept of parent functions. What are these fundamental building blocks?
Parent functions are like the simplest possible version of a whole family of functions. They're the basic, unadorned, stripped-down model.
The original blueprint.
Exactly. Like fxx is the parent of all linear functions. Fxx by 2 is the parent of all quadratic functions, parabolas. Fxx is the parent of absolute value functions.
And knowing these helps us understand the more complicated versions.
Immensely. If you know the shape and key properties of the parent function, like its domain, allowed inputs, range, possible outputs, where its zeros are, its end behavior, what happens way out at the sides, any critical points like vertices or asymptotes, then you have a fantastic starting point for understanding any function in that family, because the others are just transformations of the parent.
So the guide lists quite a few parents.
It does. Linear x, quadratic by 2, absolute value x, square root x, cubic by 3, cube root, the basic rational function 1x, another rational 1 by 2, exponential bx, logarithmic, log x, and even step functions like the greatest integer function ex.
Okay. And speaking of transformations, once we know these parent functions, how can we manipulate them to create all the other functions we've been talking about?
That's the magic of transformations. They allow us to take the graph of a parent function and shift it up, down, left, or right, flip it over the axis, or stretch or compress it vertically or horizontally.
And the guide breaks these down nicely.
Yeah, it helpfully divides them into transformations that happen outside the main function operation, which affect the graph vertically, and those that happen inside, modifying the x directly, which cause horizontal changes.
Okay, can you walk us through some common examples? Let's start with the outside or vertical changes.
Sure. If you take your parent function, fx, and add a constant b outside it, like fx plus b, that shifts the entire graph vertically upwards by b units.
Makes sense. And fxb.
Shifts it vertically downwards by b units. Easy enough.
What about multiplying outside, like a fx?
Multiplying the whole function by a constant a causes a vertical stretch or compression. If the absolute value of a is greater than 1, it stretches the graph vertically, pulling it away from the x-axis. If a is between 0 and 1, it compresses the graph vertically, squishing it towards the x-axis.
Okay. And if a is negative?
A negative sign out front, like fxx, reflects the entire graph over the x-axis, flips it upside down.
Got it. So outside changes affect the y values, up-down shifts, vertical stretch compress, x-axis flip. Now, what about the inside or horizontal changes affecting the x?
These ones sometimes feel a bit counterintuitive. If you change the input to fx plus b, adding b inside with the x,
You'd think it shifts right, but...
it actually shifts the graph horizontally to the left by b units, and fxb shifts the graph to the right by b units. It's the opposite of what you might first guess.
Okay, gotta remember that. Inside horizontal shifts are opposite the sign. What about multiplying inside fax?
Multiplying x by a constant a inside the function causes a horizontal stretch or compression. And again, it's kind of backwards from the vertical case. If the absolute value of a is greater than 1, it actually compresses the graph horizontally towards the y-axis by a factor of 1a.
Whoa, okay, so f2x squeezes the graph horizontally.
Exactly. And if a is between 0 and 1, like f12x, it stretches the graph horizontally away from the y-axis by a factor of 1a, so in this case by 2.
Definitely counterintuitive. Stretch compression factor is 1a horizontally.
Yep. And finally, putting a negative sign inside with the x, like fx, reflects the graph horizontally over the y-axis, flips it left to right.
Okay. Understanding these transformations gives you a powerful toolkit for graphing and analyzing a huge variety of functions just by knowing the parent and seeing what shifts, flips, and stretches have been applied.
It really does. It connects everything back to those basic parent shapes.
Wow, we have indeed taken a deep dive into a vast landscape of pre-calculus fundamentals in this session. I mean, starting from the basic elegance of linear and quadratic equations.
All right, the lines and parabolas.
All the way through the intricacies of rational functions with their asymptotes and holes, the rapid change of exponential and logarithmic functions, and then seeing how we can combine and manipulate all of these with operations, compositions, inverses, and transformations.
It's quite a journey.
Yeah.
But it lays such a crucial foundation.
Absolutely. And it's so important to remember, like you said earlier, this isn't just abstract mathematical theory disconnected from reality.
Not at all. These foundational concepts are absolutely essential for understanding more advanced mathematics like calculus, differential equations, linear algebra.
And they have direct applications in countless fields, right? Modeling physical phenomena in physics and engineering, analyzing growth and decay in biology and finance.
Even in computer science, economics, statistics,
Mhm.
the list goes on. These are the mathematical tools used to describe and predict how things work.
So, for you, our listener, we highly recommend revisiting that pre-calculus equations and answers guide or whatever resources you're using with this overview fresh in your mind.
Yeah, you might be surprised at how much more clicks into place, how you start to see the connections between these seemingly disparate concepts, how logarithms undo exponentials, how transformations apply across different function families.
Hopefully, identifying those connections makes it all feel a bit less like a list of separate rules and more like a coherent system.
Exactly. And this leaves us with a really interesting question to ponder, something to think about after this discussion.
Okay?
Considering how all these different types of functions, linear, quadratic, rational, exponential, log, are interconnected, how they can be transformed, and how their graphical representations visually tell their story. What new perspectives do you now have on how mathematical relationships can be used to model and understand the complexities of the world around us?